Welcome to the Here Education module. What are environmental exposures and how can they enhance my study? The objectives of this module are to introduce environmental exposures, describe how biological specimens could be used to assess environmental exposures, highlight examples of which environmental samples are used for environmental exposure analysis, and finally, describe why including environmental exposure data will enhance a study. Let's begin with answering the question, what are environmental exposures? Environmental exposures are exposures that include the chemicals and compounds we come in contact with within our environment, our air, soil and dust, water, or food. Exposure to these contaminants generally occurs by one of three exposure routes: ingestion, inhalation, or dermal contact. While environmental exposures can cause acute illness, it is important to understand that some environmental exposures may increase the risk of certain diseases, such as heart disease, cancer, and respiratory diseases. Adverse health effects caused by environmental exposure will depend on several factors, including the type and amount of chemical an individual was exposed to, the combination of chemicals, the route of said exposure, the duration and frequency of the exposure, and even at what age or life stage someone is exposed. These environmental exposures to air pollution, contaminated food and water, and toxic substances, especially early in life, can affect development at all critical life stages, from embryo through childhood and into adolescence. Now that we've discussed what environmental exposures are and the routes of exposure, let's talk about factors affecting an individual's susceptibility to health outcomes of interest. For example, an individual's life stage might affect his or her susceptibility to chemicals or pollutants. Different population groups might experience varying susceptibilities. There are both intrinsic and extrinsic, or acquired, factors that affect an individual's susceptibility to contaminants. Susceptibility factors for individuals include life stage, gender, genetic polymorphisms, socioeconomic status, disease status, nutritional status, geographic proximity to sources of exposure, and various lifestyle choices. Additionally, toxicokinetic differences among individuals affecting how easily a chemical is absorbed, metabolized, and excreted are also important factors. In addition to personal susceptibility factors, behaviors and geographical location influence what, when, and how much of the environmental contaminants someone is exposed to. At a population level, factors to consider that could affect exposure include disease status, socioeconomic status, diet and nutrition status, geographic proximity, and lifestyle. When researching environmental exposures and health outcomes, be sure to consider how some population groups may be predisposed to higher exposure rates than the general population due to cultural or economic factors. A few examples of social and behavioral influences on environmental exposures include populations in locations that use cook stoves for meal preparation that are exposed to the air pollutants from the stove. Young children who are more likely to be exposed to dust and soil than adults since they are frequently on the ground and put their hands in their mouths. And communities using well water in areas with naturally high occurring arsenic are likely to have higher levels of arsenic detected in their blood than communities with very low arsenic levels. Remember, when we talk about environmental exposures, the term environment can include pesticides and other agricultural chemicals that may find their way into our food and water, geogenic toxins, personal care products like cosmetic and sunscreens that we put on our skin, industrial pollutants in the air we breathe, and chemicals found in the products and building materials we use, pharmaceuticals, and the influence of lifestyle factors such as smoking, secondhand smoke exposure, stress, and nutrition. Analysis of these external exposures, biological responses, and host susceptibility can help establish links between environmental exposures and health outcomes. When studying environmental exposures, there are two main types of laboratory approaches. First is the targeted approach, in which compounds and chemical elements of interest are specified. The second is the untargeted approach. This is more of a discovery approach or a hypothesis-generating approach to identify what compounds are in the samples. To provide further context, a glossary of some key terms to support measuring environmental exposures includes terms from the Dennis et al. 2017 article in Environmental Health Perspectives. Again, targeted analyses will analyze biological samples for specific chemicals, which can be either exposures or markers of exposures. Untargeted analyses use techniques to promote identification of unknown and emerging exposures of concern, and aims to measure biologically meaningful lifetime exposures, both exogenous and endogenous. This untargeted approach enables detection of features that are linked to exposure or disease for further confirmation. And semi-targeted analyses combines targeted and untargeted approaches. As an example, this can be done using metabolomics for discovery of potential exposures, followed by targeted analysis for a more fully quantitative measure. So far, we have established what environmental exposures are, routes of exposure, and approaches to analysis. But we are exposed to a variety of chemicals and compounds throughout our lives. So you might be asking yourself, what about the cumulative impact of these exposures? Well, this is the concept of the exposome. The exposome is defined as the totality of exposures throughout the lifespan, from conception to death. Wild, 2005. The exposome includes the cumulative measure of exposures to both chemical and non-chemical agents such as diet, stress, and socio-behavioral factors. Measurement of the exposome includes a series of quantitative and repeated metrics of exposure, both from internal and external factors, that describe holistically environmental influences or exposure over a lifetime. Exposomic approaches go a step beyond traditional biomonitoring, with the aim to capture all exposures that potentially affect health and disease. This includes untargeted discovery of unknown chemicals of biological importance. The wide range of exposures occurring over the life course highlights the importance of answering the question, what is the role of environmental exposures affecting human health? Here, the Human Health Exposure Analysis resource measures human environmental exposures, including chemical, physical, and biological stressors, lifestyle, such as nutrition and smoking, as well as measurements of environmental exposures within different social environments. This is done measuring biomarkers and environmental samples for targeted and untargeted analyses. Here can measure environmental exposures through a variety of biological specimens, including urine, serum, plasma, whole blood, cord blood, breast milk, hair, dried blood spots, saliva, and teeth. Environmental exposures can also be measured using environmental samples, such as water, air, dust, soil, food, and silicone wristbands. Note that here also accepts these environmental samples for applications, but this module provides a greater focus on providing information for biological specimens. If you have biological specimens and you are interested in environmental exposure analysis, it is important to first think about what types of samples you have available, including how much is left or available for further analysis, the collection methods, and storage conditions. Consider the time of sample collection. At what time point or points did you collect samples? For example, if there were multiple collection points over time, longitudinal, and potentially across various life stages, the study could assess for when people were exposed and if exposures are cumulative. This is a sample matrix of laboratory services available by HERE. You can visit the HERE website for a more exhaustive list of analyses available by matrix. Note that on the left are matrices for clinical biospecimens, such as urine and blood, and on the right are environmental matrices, like water, dust, and silicone wristbands. For assessment of biological specimens, additional points to consider are the half-life of the compound in media, which can be an important parameter to determine the extent of bioaccumulation or biological concentration, the number of freeze-thaw cycles for the available samples, and the number of specimen collections, which could be used to inform a temporal component in the assessment. If you have questions about assessments, reach out to the HERE Coordinating Center at herehelp@westat.com to schedule a consultation. Let's explore an example. If childhood behavior is an outcome of interest in your cohort, you could look for environmental contaminants that may be associated with childhood behavioral problems. Exposure to phthalates, for example, has been associated with reproductive developmental and neurotoxicological toxicity in humans. Many studies have linked prenatal exposure to phthalates with adverse health outcomes in newborns and children. Phthalates have been used as plasticizers and solvents over the past century. Phthalates are not chemically bound to the products they are added to, so they are released into the environment and enter our bodies through inhalation, ingestion, and dermal absorption. Phthalates have a short half-life, less than 24 hours, and they have been detected in human urine, blood, feces, amniotic fluid, breast milk, and sweat. If you want to add this type of analysis to your study, you would want to ensure you have the necessary sample quality and quantity to measure phthalates. Typically, 1/10 of a milliliter to 1 milliliter of urine or 1 gram of dust are used. Smaller volumes can be used, but usually translate to lower frequency of detection. Samples must not have undergone repeated freeze-thaw cycles and must have been collected to minimize phthalate contamination. A study design may perform separate analyses for several phthalate metabolites. Note that there is growing evidence that measuring the presence of multiple phthalates as well as additional chemicals will more accurately measure health risk compared to measuring individual phthalate concentrations. Now let's look at an example of how environmental exposure data can enhance studies when Alzheimer's disease is the clinical outcome of interest. Studies have demonstrated that the legacy pesticide DDT is associated with Alzheimer's disease. Exposure to DDT in people likely occurs from eating foods including meat, fish, and dairy products. While the United States banned the use of DDT in 1972, some countries still use DDT to control mosquitoes that are vectors of disease such as malaria. DDT and its metabolite, DDE, is typically measured in serum and persists for a long time in the body and environment. While research has demonstrated associations between DDT and Alzheimer's disease, there are still opportunities to further explore other environmental contaminants that might be associated with a cohort with Alzheimer's disease. Again, targeted and untargeted approaches can be used. Individuals are continuously exposed to chemicals, microbes, and pollutants from the environment. These exposures have the potential to exacerbate disease, interact with our genes to promote disease, or alter metabolic processes. Including environmental exposure analysis when studying dynamic human health outcomes serves to create a more robust study result. Looking beyond one study, once we analyze study results, data from numerous studies can be harmonized to provide a better understanding of how health outcomes are associated with environmental exposures, subsequently informing health risks. Merging data across different cohorts that have focused on shorter windows or specific life stages is an approach to simulate the life course and explore changes in the exposome over time. This figure shows how exposure is linked to health endpoints. Using advanced exposure science technologies, including omics, within each critical life stage, and then integrating the results across life stages gives a life course view. Additionally, participation in the HERE program is an opportunity to add to the HERE data repository, which is a valuable harmonized resource. The HERE Data Center repository holds all data generated by the HERE Lab Hubs, along with pre-existing epidemiological data provided by HERE study principal investigators. After an embargo period, the HERE Data Center will provide publicly accessible, de-identified datasets. These data include, but are not limited to, the environmental exposure biomarkers and environmental exposure data, previously collected epidemiological data such as key covariates like sex, race and ethnicity, age, and education, previously measured biomarkers, including clinical biomarkers, genetic data, and health outcome information. Please visit the website linked on this page for the most up-to-date data from HERE studies. If you are interested in learning more about how your study samples could be assessed for environmental exposures, HERE has several resources to help. HERE provides consultative services that you can take advantage of in the early stages of developing a proposal. In addition to expert consultations, HERE offers state-of-the-art lab analysis and statistical analysis support. HERE even has special techniques to look at longitudinal data. And again, HERE has a growing repository of epidemiological and biomarker data. Contact the HERE Coordinating Center at herehelp@westat.com to request a pre-submission consultation. During this meeting, you will be connected with scientists from the HERE Lab Hubs or Data Center to address your inquiries. Finally, we have provided a list of links to additional environmental exposure resources. We hope you found this module useful.